All right, let us begin. This is a problem that relates the effect of a net force on an object, the resulting acceleration that comes from that net force, and the motion that that object undergoes due to the net force. That net force causes some acceleration. That acceleration causes the velocity to change. How much does it cause the velocity to change? That determines or depends on the amount of time in which this net force occurs on the object. All right, so we're going to try to show the relationship here. This is problem number 773 on page 116. I encourage you to solve this problem or attempt to solve this problem on your own before watching this video. We have a jet airliner or an aircraft that's represented by my box here. That's my aircraft. And it's moving to the right. It's moving to the right from rest. And eventually, as it's moving to the right from rest, it'll reach its takeoff velocity. Its takeoff velocity I labeled as v sub t, which is 285 kilometers per hour. It's able to reach that takeoff velocity from rest because it has some force of thrust that's acting on the aircraft from the jet engines. This is the amount of thrust that those engines produce. We also know the weight of the plane. I labeled as W sub p. Each of these parallel lines, of course, mean the magnitude of that force. This would be the magnitude of the weight of the plane, which is 2.75 times 10 to the 6 newtons. The thrust that's generating our change in velocity here, or our acceleration, is 6.35 times 10 to the 6 newtons. What we're trying to find is, what is the minimum length of runway needed of runway. In our case, that corresponds to the quantity of displacement. So eventually it'll reach this point here where it's ready to take off. How far did it travel in going from rest at the start of the runway to the end of the runway? To conceptualize this problem, before we begin solving it, we have some net force generated by thrust, some net force coming from thrust. Okay, this is from the fact that there's some thrust acting on this object. Because we have a net force or a thrust vector that's occurring here, specifically because of the net force, then we see a change in velocity. By change in velocity, we mean acceleration, right? There's some average acceleration that occurs because of that. We know that all because of Newton's second law. Newton's second law tells us if there's some net force, which in our case comes from thrust, then we're going to have a change in velocity or some acceleration. That acceleration is what's going to get us to our takeoff velocity. We're going to see, well, in going to the takeoff velocity, it traveled some distance here. Some distance, what distance was that? What distance or change in position is needed? There's the minimum change in position that this aircraft must undergo in order to reach its takeoff velocity. All right, so our strategy here, we can start with our kinematics. That's always a good place to start because we see that we're trying to find the minimum length of runway. So we'll start with our tools of kinematics. What do we know about the motion of this object? It's helpful to start with a known and unknown chart. What do we know about the motion of our aircraft? What do we not know? What do we need to find? Well, we know the initial velocity of the aircraft is 0 meters per second because the aircraft is moving from rest. The final velocity is something that I just put it in the unknown column. We know what the final velocity is. That's the takeoff velocity. Final velocity and the takeoff velocity are the same, and that's 285 kilometers per hour. There's immediately a problem here that we see. Wherein our takeoff velocity is in the units of kilometers per hour, we're very accustomed to meters per second. We can't use kinematics variables that differ in units. They all need to be in meters, or they all need to be in kilometers, or they all need to be in hours or seconds. They all need to be consistent with each other. All right, we don't know the acceleration that our aircraft undergoes. And we also don't know the length of runway, the displacement that it goes through in reaching this final velocity, this takeoff velocity. Ultimately, we need to find this displacement. Before we can find this, however, we'll have to find the acceleration. So we're at an impasse here. We must now turn to forces. We'll begin analyzing the forces that are acting on this aircraft. And maybe from forces, we'll be able to find what the acceleration of the aircraft must be. To start, we'll use a free body diagram. To start our free body diagram, we draw a dot. The dot represents our object that we're analyzing, in this case, the aircraft. What forces are acting on the aircraft as it moves along the runway? Well, we have the weight, of course, of the aircraft. Here's the weight of the plane, which we know the magnitude of the weight of the plane. We know that's right here, 2.75 times 10 to the 6 newtons. There must be some force that responds to that weight, the force that the wheels, or that the ground puts on the wheels that hold up the aircraft. We call that the normal force. And then we have this force of thrust that's sending the aircraft to the right in order for it to reach its takeoff velocity. That's what's causing our acceleration, our change in velocity, is this thrust vector. We're going to ignore any drag or friction here. All right, so here's an appropriate free body diagram. The forces we're concerned with are those in the horizontal or x dimension, in this dimension right here. The only force there is thrust. So we'll look at the sum of the forces in the x dimension. Those forces in that dimension that's causing it to reach its takeoff velocity. The only force is the force due to thrust. That force of thrust, that's all the forces. F equals mass times acceleration, or the net force equals mass times acceleration. This is the mass of the plane because this is the force acting on the plane. We'll call the thrust force acting in the positive direction. We'll label this as mass of the plane, and then the magnitude of the acceleration that the plane goes through. This acceleration here is the same average acceleration that we're trying to find here. So I'll relabel that for us to make it a little more straightforward. This is average acceleration. This is still the force of thrust on the aircraft that's causing some acceleration. Okay. We know the magnitude of the thrust. We don't know the mass of the airplane. We need some way to relate the mass of the airplane, the aircraft, to we need some way to find the mass of the airplane. What we do know is the weight of the plane. So really this arrow should be, we know the weight of the plane. From the weight of the plane, we want to see if we can find the mass of the plane. And we can. The relationship between weight and mass is the gravitational field. That's our relationship. We know that the weight of any object is the mass times the gravitational field that that object's in. We'll apply this to our situation. We have the weight of the plane. Weight of the plane equals the mass of the plane times the gravitational field the plane's in. We know the weight of the plane. We know the gravitational field the plane's in. We just need to find what the mass of the plane would be, so we can divide both sides by gravitational field. What we're left with is that the weight of the plane divided by the gravitational field is the mass of the plane. All right, let's take the weight of the plane, which is 2.75 times 10 to the 6. That was provided in our problem. We know the weight of the plane, divided by our gravitational field, which is 9.80 newtons per kilogram. We find that the mass of the plane is 2.81 times 10 to the 5th kilograms. Oops, I'm going to rewrite this. 2.81 times 10 to the 5th kilograms. That's our mass of the plane. Now that we know the mass, we can take that quantity and put it back up here. This quantity is going to go all the way up and relate back to our equation here. Because now that we've found the mass and we have the force that's acting on that mass, that corresponds to some acceleration. All right, so I'm going to rewrite this equation over here as the force of thrust, which is causing this acceleration, divided by the mass of the plane that we just found. That gives us the acceleration that the aircraft must undergo. All I did was take this equation and rearrange it, where we just have acceleration by itself. We know the thrust acting on the plane due to the jet engines. That's 6.35 times 10 to the 6th. We just solved for the mass of the plane as 2.81 times 10 to the 5th kilograms. That brings us to an acceleration of 22.6 meters per second squared. This is the acceleration that the aircraft undergoes due to the net force that's acting on it, the thrust. So now we can take this value of 22.6 meters per second and return back to kinematics. Returning back to kinematics, now this unknown acceleration is now known because of forces. So now we know the initial velocity, the final velocity, and we know the acceleration. What is an equation that relates those three knowns to our last unknown, which is the length of our runway or the displacement that our aircraft undergoes in reaching its target velocity of 285 kilometers per hour? This is the equation that relates those four quantities together. We know final velocity, that's the takeoff velocity. Starts from rest, that's its initial velocity. We just found its acceleration, and what we're trying to find now is what's the length of runway, what's the displacement that the aircraft goes through in starting from 0 meters per second and ending up at 285 kilometers per hour. We'll rearrange this equation for change in position. I need to move initial velocity squared to the other side, and then divide by 2 times the acceleration. This gives me the change in position. Now I have one last problem here, and that is that this final velocity, this takeoff velocity, is in kilometers per hour. I need to convert that into meters per second. I could also, conversely, I could change this meters per second into kilometers per hour. I could change this acceleration into kilometers per hour squared. It's going to be easier for us to simply make one change from 285 kilometers per hour, 285 kilometers in 1 hour, to convert that using 2 conversion factors into meters per second. Right? We need to get into meters per second. First, we'll address the kilometers. Kilometers needs to be on the denominator, meters on the top, so that these two will cancel. We'll go from a really big measurement to a smaller measurement, so it's going to be split up into 1,000 pieces. For every 1 kilometer, we have 1,000 meters, so however many kilometers we have times 1,000 meters. Then we need to cancel and get rid of these hours and get it into seconds. I know for every 1 hour there are 3,600 seconds. So now we just multiply across, so 285 times 1,000 meters times 1. That gives us our numerator. Divided by what's in our denominator, which is 1 times 3,600. So we end up with a takeoff velocity of 79.2 meters per second. Let's go back now. Now we can, instead of 285 kilometers per hour, we know now that is 79.2 meters per second. I can now input those quantities into our equation here. So I have 79.2 meters per second. That quantity is squared minus 0 meters per second, my initial velocity, quantity squared, divided by 2 times our acceleration that we found as 22.6 meters per second squared. I put that into my calculator, and we find that our displacement is 139 meters. All right, what does this mean? This is our final answer. Our final answer is that if our aircraft that has a weight of 2.75 times 10 to the 6 newtons, that corresponds to some mass. That amount of mass is able to accelerate at a certain rate if the thrust that's generating an acceleration is this magnitude. We analyze those forces that cause that acceleration here. We said, well, the weight gives us some information about the mass of the plane, which is what we needed in order to find the acceleration. We found the mass of the plane, which is 2.81 times 10 to the 5th. Put that back into our equation here, which we rearranged and placed here. We found that, well, if that's the thrust and this is the mass of the plane, the acceleration, the resulting acceleration must be 22.6 meters per second squared. Then we went back to kinematics and we said, all right, now that we know the acceleration, and we knew the initial velocity, we converted the final velocity into meters per second. Then we can use our third kinematics equation and find that the length of runway, the minimum length of runway that's needed in order to have this aircraft reach its takeoff velocity of 285 kilometers per hour is a length of runway of 139 meters. All right, thank you.